Hi, everyone. My name is Yumin. I'm the CTO of Gravity by Galxe. Today, we'll talk about how to build an ultra-fast EVM blockchain without millions of dollars. So think about this. DeepSeek managed to train the state-of-the-art model without a giant hyperscale GPU cluster. And the guiding question for us is it possible to build an ultra-fast EVM blockchain without massive funding from VCs or the crowd? So our mindset are very clear. If we want to do this, we have to leverage solid open source components as much as possible. And we need to focus on measurable engineering metrics instead of buzzwords like we got building some kind of another AI chain. And another goal is we're going to build this for public good instead of some kind of alien technology hype. All right, so many people consider building blockchain not rocket science. I agree, but it's neither trivial. So under the hood, there's a lot of things. So this is a traditional blockchain architecture. There you see all these components actually has a lot of practical innovations that we need to do to reach very high performance blockchain. So for example, for execution, people always talk about parallel execution, and we want to do JIT or AOT to speed up the execution. And for storage, you may consider to employ a fully asynchronous I/O storage, and you have choices between RacksDB and DBX. And for consensus, there's also research and studies for new consensus algorithms as well. So to start with, let's start by choosing the right consensus algorithm. So our criterion is we wanted this chain to be so-called sub-second finality with more than 100 validators. We want it to be high throughput for independent transactions, meaning that, for example, your Uniswap transactions. We want it to be production ready and bottle test the implementation, and we want to get it done within 12 months. So we explored all options. Like on the PBFT family, you got Tendermint, Hostile, Jortian, Aptos BFT, and there's a lot of fancy DAG-based consensus algorithms as well. So it turns out that Aptos BFT is a champion after our exploration. So some insight about Aptos BFT. So Aptos BFT is an improved version of Jortian consensus plus the optimization called order votes, which reduces the consensus latency to 3 hops. And for people familiar with consensus protocols, to reach PBFT, to reach BFT, actually the minimal theoretical liminal lower bound is 3 hops. And Aptos actually, their code, their implementation has the highest records on production. In last summer, they have 300 million user transactions in a day, which averages to 3,700 user transactions per second over the whole day. They have more than 150 nodes, and their block time, meaning the gap between generating 2 blocks, is around 220 milliseconds. And in their latest research, the end-to-end latency is around 380 milliseconds plus the client latency depending on where you are. And the bonus is that they actually did a bit of research on how to provide an instant on-chain randomness. If you are interested, you can read their paper. But in general, that means that you need any oracle. Your blockchain validators also generate a variable randomness upon your request. So as they are also rapidly developed and innovated, there has been more than 100 AIPs pushed to production, not just draft. And now some people ask, like, why not draft? Why not DAG-based consensus algorithm? So the reason is that in a scenario for DeFi transactions, all these transactions are interdependent, meaning that the stack-based transactions, the fast path that you don't need to run through a total ordering doesn't work. All right. Although the state-of-the-art consensus can hit some bottleneck, so the novel paper actually revealed a very interesting insight that the leader node's network I/O is actually a major bottleneck. If you look at the diagram on the right side, the light blue one is the hostile algorithm without solving the I/O issue. The TPS is somewhere less than 10K, or maybe just even smaller. But the darker blue one is the one that you actually solving the network issue, that you easily reach 50 or 75K. So what Aptos does is that they introduce a very simple and elegant mechanism called a quorum store, meaning that validators basically pre-share transactions into batches, and validators form a quorum store, proving that they have stored all these transactions already, so that when leader proposes a block, they only need to propose the proof of availability of those batches. And then upon execution, validators can always fetch transactions from other validators. And even more surprisingly, this mechanism, even being very simple, can be horizontally scaled, which meaning that you can actually have infinite TPS you want. So this is a diagram we also got from the Novel paper that with more workers per validators, your TPS can actually reach a very, very high level. On the right-hand side, you can see that with 10 workers per validator, if you are running narrow with hot stuff algorithm, you can actually have, I think it's around 600K TPS. Okay, besides the consensus, what Apple's also innovated is the pipelining architecture of a blockchain. So traditional blockchains, like the diagram I showed before, you first do transaction dissemination. You get all these transactions. Validator propose a block that contains all these transactions. But in a pipeline world, consensus can be run independently with execution. So in this case, when block 100 is actually certifying all the changes, meaning it's generating its Merkle proof, the block 101 is actually doing execution, and the block 102 is actually still running consensus. So that means that with pipelining, you'll be able to reduce the latency. So for example, let's see consensus takes 200 milliseconds, execution is 500, commitment is 300, and percentage 100. For traditional non-pipeline blockchain, it will take almost like a second to finish a block. But for pipeline architecture, it's only the slowest stage, which is 500 milliseconds. These benefits actually coming from much higher resource utilization, where in consensus, most of the resources are spending on network I/O, and when in execution, it's CPU bounded, and storage is just disk write. And so, let's say Aptos has already built this solid ground. Can we modularize Aptos? The answer is, of course, yes. So that's why we built Gravity SDK. So Gravity SDK is an open source modularized blockchain framework that's designed to be scalable and flexible. We do that by modularizing Aptos bottle-tested components. And that means like in this Gravity SDK, you get Coron Store, mempool with Coron Store for free. You get Aptos BFT with very low latency. And you get this pipeline architecture. So this is also the first of its kind, like pipeline the blockchain SDK as we know. And it's very easy to use. We don't want developers to know all this detail of pipeline blockchain. So that's why we build Gravity Consensus Engine interfaces. So Gravity Consensus interfaces basically abstract out the whole consensus process from building a blockchain, that the developers, basically, you only need to implement all these 4 interfaces, that you tell consensus, well, is this transaction a potentially valid transaction upon the current stage? And you send transactions to consensus, then you will use mempool and Coron Store to broadcast it. And once consensus order those transactions reach the block, you will send this order block to execution layers. And execution layer, after executing all these transactions, you will send back the block hash. And the consensus will run another set of finalization upon the block hash, which the whole process also piggybacked on the Aptos consensus. And once it's finalized, we'll basically commit and persist in every result. So if you're looking at from the pipeline, the architecture will be like this. We're building a middleware called execution channel, where on the execution side, you basically, for each stage, you build a pipe. You build an internal queue or buffer or pipeline that transactions are sending through the channel to the consensus engine. Consensus engine continuously produce blocks to your execution engine. Your execution engine consume all this blocking order in your execution queue. And once you've done that, you send it back to the consensus engine and send back to the certified blocks commit, and you persist it. So Aptos SDK is not just the idea. We've already built it for the past 6 months. It's fully open source, although it's still, we call it a pre-alpha version. But our initial benchmark is already very impressive. For simple concepts like row transfer, we reached 120,000, it's a 12,000 TPS. And for block count, with our default configuration, it's less than 500 milliseconds. So that you can find the code here. We also built a demo project, a demo chain that is a simple key value store with Ethereum style account. You can find it here with less than 1,400 logs. Now you may ask, like, well, this is a very simple example. Why do we want to build an EVM blockchain? So that's what we did. So basically, we built upon REST. REST is the fastest Ethereum execution engine, and it's highly optimized. So the challenge we faced is that REST is a traditional non-pipeline blockchain where things go just one by one. We introduced a pipeline execution engine called block string reactor that taking ordered block from the consensus engine, then execute it in a pipeline manner for all these stages. And you can find our code here. And there's also some other challenges, but due to the time limitation, I'll probably not cover. So the next is, let's say we solve the consensus and pipeline issue. Our next target is the slowest stage of the pipeline. Remember that I said the execution is usually that one. Recall our goal of 1 gigagas per second. So an example is that if you want to have 1 gigagas block for full Uniswap transactions, it's actually today, even you are running REST, it's going to take you 700 milliseconds. And this is under the assumption that the I/O latency is 0. In the real world, a 100 microsecond latency is actually very usual. So if in that case, the sequential execution actually can take 24 seconds. So that's definitely way slower than we expected. So that's why we need parallel execution and asynchronous I/O. So for parallel execution, it's actually a well-studied algorithm called block STM. So what block STM does is so-called parallel optimistic parallelization. In a very simple word, it basically executes a transaction all in parallel, all at once, as much as you can. And then you started the validation phase that start to validate the transaction from the beginning. So now first transaction, everybody knows that it's not going to have any conflict. And the second transaction basically check, well, does it conflict with the first one? And then the third one checks with all these transactions that has been executed before. And surprisingly, to many people's surprise, the block estimate is actually very, very fast, even it's optimistic. So in their papers, they can actually reach 160,000 TPS. And the slow overhead is actually pretty low in a pure sequential workload, meaning that there's no opportunity to parallelize anything. The overhead is only 30% slower. Not just block STM, we actually did some interesting follow-up work based on block STM. So we call this Gradient 2.0, stand for Gravity Rust EVM. So instead of like we're following the block STM style that we basically schedule all these transactions one by one, starting from the lowest index, we actually schedule those transactions in parallel using the DAG. So this DAG can actually be obtained by simulating transactions in some other stage of the pipeline, fully shadowed under the execution. And then in this stack, we basically try to parallel execution transactions that has 0 dependency and the lowest index. And besides that, we introduce another mechanism called task group, where because we noticed that actually on the Ethereum mainnet, we look at all these history transaction data. There are many, many transactions that depending on each other tightly. So in our data, we will publish a paper very soon, but in our data, the P50 dependency distance between transactions is 2, meaning that most of these transactions have dependencies next to each other. So what task group is that it will basically, in the stack, merge those nodes that has tight dependencies into one task group. Then when we dispatch those transactions, we basically dispatch them as a group. So group transaction within the group won't be executed parallelly, but sequentially, so that the latter transaction can correctly read the data that was right by the previous transactions. This effectively reduced the re-execution as the overhead. So the benchmark is also very good. These algorithms can actually match block estimate performance for the most ideal case that independent transactions, which is definitely more than we need. And for high content workload, we put a transaction that has 30% transactions that depending on each other. It is like 29 times speed up, maintaining at least almost like 3 gigagas. And for non-parallelizable transactions, this mechanism nicely solved the drawback from block STM, the 30% slowdown. We achieved only 3 to 5% slowdown than sequential execution. And because the re-execution is much reduced, we have 95% lower CPU usage if you just run block STM. So another thing that we found during this journey is that optimistic parallelism is actually way more effective than most people expected. So combining this, we have gravity chain. So the life of a transaction in Gravity chain is that you first reach through JSON RPC, and it reaches the mempool and quorum store, and the leader of the consensus will propose a block and send it to our parallel execution engine. Then it will generate a new state that runs for block hash, and the block hash will run through another state consensus. And after all that, it will push to the storage for persistence. Yeah, so our next big release about restaking module. So remember, initially we thought we want to build a proof of stake blockchain. And one concern we always had is well, most proof of stake blockchains ask you to stake their own native token. I know this kind of was operated in a lending model or whatever, but we think it's not ideal. So by introducing restaking, we allowed other other validators or economical security to be brought on Gravity chain. So we were integrating staking protocols like EigenLayer and Babylon, which allows us to tap into Ethereum and Bitcoin's security level. And in the next release, we'll also introduce Aptos' recent optimization called Aptos, that they shadow all the executions by each other using optimistic tricks. Yep. So with that being said, with Gravity SDK, we believe that this is the first of its kind pipeline blockchain that reaches very, very high performance. With this kind of performance, we believe we can decentralize a lot more things than before. Feel free to come around and discuss and throw critical questions to us. You can feel free to also follow our Twitter here and also scan the QR code. Thank you.